Okay, here's my clicky button. Very good. All right, thank you. Yes, my name is Laura Schulz. I'm head of quantum computing at Leibniz Supercomputing Center. So getting started right away, I want to talk first about HPC before we delve into quantum. So this, for the last 15, 17 years of my career, this has been my reality. This is what our HPC center, our compute environment at LRZ looked like just a couple of years ago. So very much used to dealing with very large-scale hardware, really pushing the compute environment and the capabilities that we develop, this technology that we provide, so that our researchers can really push the envelope for what they're discovering on their scientific journey. Modeling and simulation has been around for decades at this point. We have won a lot of battles. We have big war bruises and war stories to tell about the continuous integration, the continuous implementation of progressive technology with HPC, and how we are able to squeeze scientific results that are faster, more complex, more resolution, to continue getting us to our scientific discovery even further and getting those results. So this is what HPC looks like, what we are very expert in and has been for several decades. Now, a couple of years ago, we were part of a beginning initiative with the Munich Quantum Valley. This is an endeavor from the high-tech agenda in the state of Bavaria. And with this, the government put in, really committed to 300 plus million euros, plus there was another many million euros coming in from the federal level. The whole idea was to genuinely take the brain power, the capability, the experience of the Bavarian ecosystem from institutions like Fraunhofer, from Max Planck, the Technical University of Munich, LMU, Bavarian Academy, which is our flagship institute, pull all these together and to really develop quantum technology, Bavarian-born, focusing really on superconducting, on neutral atoms, but then not just that, but it was also integrating it into the HPC ecosystem to really make it part to support that technology, to provide, again, as I said, that background, that expertise from HPC, and to bring those two together. So that really brings me first to the point, okay, so why HPC-QC? Again, for me, from an HPC perspective, I see quantum computing as high-performance computing. This is another layer, another story in the chapter of supercomputing. Over the history of advanced compute, we have had different technologies fold in to this entire ecosystem. Obviously, with the other part of this conference going on, with AI, with the invent of GPUs and the movement of them from the graphics and simulation, or graphics environment into HPC. We've brought all of that in. We found a new way to enhance and expand our compute capabilities. We see the same thing with quantum, and it's very exciting because, and I won't go into this now, but we are reaching certain limits on the spectrum of high-performance computing. There's only so much that we can do for the engineering of CPUs and of GPUs. We're facing natural laws. We're hitting really the certain walls of physics. There's only so much that we can do with the technology that we have now. Quantum computing is fascinating for us because we're applying a whole different paradigm of physics to this fight, to this computational fight. So QPUs, quantum processing units, are really intriguing to bring into the fold of HPC. Now, we do not expect, and we know that it is not going to replace HPC as we know it today. It is going to enhance it. Just like with GPUs, there are certain calculation behaviors, characteristics, where a QPU is going to absolutely excel. And so we want to take that particular capability, that particular computational behavior, and apply it to this whole ecosystem and really maximize what we've already accomplished, replace some of the work that we've already done with QPU computation, and really, again, advance forward as we move on. So this picture, so that picture beforehand was a graphical, a nice rendition from our designer. This is our reality, and this is basically a superposition of where we currently are and where we're going. This is our Q-Exa system, and it is seated in our compute center at LRZ. This is from the Finnish-German company IQM. It is a 20-qubit superconducting system, and as you can see, it is placed right next to our racks of our HPC systems. This is where we are currently at. I'm going to talk a little bit more about this, but we, as Matthias mentioned this picture already, we inaugurated this system in June of this year, and we ran our first successful run, variational algorithm from the HPC environment all the way through, hitting the quantum system, calculating, bringing those measurements back, running back through the HPC environment. So we had a full run, which represented a really fantastic milestone for us because we were able to bring all these components together, get them working in unison, and be able to accomplish this. Now, this is not our only system at LRZ. This is our current portfolio, or our coming portfolio. We're pretty heavy on the superconducting side. We've got a 5 and a 20 qubit system for our R&D center, which I'll talk about a little bit later. We have our 20 qubit, which I'm going to call our production, because that's in our compute cube space and falls under different operational parameters. We've got 2 systems coming next year and the year after. That'll be announced before too terribly long, but this is going to be a 50 and 100 plus system. That's on the superconducting. On the other modalities, we have an ion trap system from the Austrian company AQT. That's also a 20 qubit ion trap system. And then we've got a 1,000 qubit neutral atom system coming from the Planck team in a couple of years. So, and of course, I'm always looking to add on and how we add on. This presents our portfolio. And again, being that we're early in the evolution of all of this, we can't put our eggs in one basket. So we have superconducting, we have ion, we have neutral, we have other modalities coming. And we have that because we're at a very early evolutionary phase in this development where we see that we don't know who's going to be the winner. I don't think that there's going to be one winner. I think there's going to be a suite. And we're going to find, as we continue to move on with those applications, which ones are best suited for different types of compute. I would like to see a really nice ensemble here of capabilities, which presents us with a couple of problems that I'll get to in a moment. But to this point, our center represents a bit of a microcosm of what we're seeing all across Europe. So we are also very proudly a partner, a member of Euro HPC. We were awarded for Germany to be the ones to seat a quantum system from Euro HPC in our center. That's what I mentioned, the 50 and 100 before. And again, we're doing this with 5 other partners, 5 other partner countries, and we all have different modalities, okay? Fantastic. So we're bringing those systems out of the physics labs, out of the startups. We're putting them in HPC centers. And Euro HPC really, to their credit, has said not only here's a quantum computer, but they've said, but now your mandate is that you have to connect it to HPC workflows and you have to run hybrid compute together. So they really threw down, and really to their credit, they're the first government to really do this. And so this really puts the onus on us to figure out how to implement this. We have to think about the users, because for the users, all these different modalities, all these different HPC centers, this is going, if we're all going to evolve in our different pathways or are on our unique paths, we're not going to be serving the users at all. So this is requiring us to work together in a way, in a really, really tightly integrated way together, to make sure that we are providing, that we're bringing up these systems, that we're helping to advance this technology, that we're connecting it to HPC centers, and that we're doing so in a way that the users will even want to use it and will adopt it. Which gets me to this point, and that's kind of the first, I don't want to say problem, but it's the challenge, the opportunity that we have, that these modalities are different. So they have different operational parameters, they have different figures of merit. They have different compute behaviors. Some can cohere longer than others. Some are more stable than others. Some you can scale more than others. Some communicate between the qubits in a different fashion. They all have their different personalities, right? And what we have to determine is what personality is going to fit best for the application or part of an application that we're working on. So that's one thing that we have to keep in mind with all of this. Now, the second thing is that they are sensitive. All right, so for folks that would be in HPC space, in quantum we talk about 3 nines, 4 nines, heaven forbid 5 nines moving forward. HPC, 3 nines, 4 nines, the nines, that was back in the 40s, 50s, 60s. That's not a problem, that level of stability. Here in quantum, it is a problem. They are sensitive to their environment. They do decohere. They're not as stable. This is just a reality of the systems. And I want to give you an example of this because on our signal chat with a company, we got a text message one day that said, hey, I see large magnetic field changes. Is anything going around? Anything going on? And one of my operators from our integration center, he sent this picture and he goes, well, I moved this ladder from point 1 to point 2. And it was picked up on the quantum system. Okay, these are incredibly powerful sensors, right? And when we bring a quantum system into our environment, we're working on hardening them. We're giving them information. We're giving the companies feedback. We're having this problem. Maybe for your next form factor evolution, you should think about more shielding. You should think about this. You should think about that. They're coming in. They're seeing their own issues, things that they want to account for their next evolution. But I think that there's going to be only, in my opinion, there's only going to be so much hardening that we can do. There's only going to be so much, HPC center compliancy. We have to honor what these systems are and their physics, and we have to account for that. So one thing that we do, we have a big telemetry study going on where we've basically IoT censored our lab environment, this quantum integration center. We've censored it with a whole bunch of different sensors. Here's a couple of them here. But the idea is that we want to collect all of this data. We want to see how the system is performing within the data. We take the job runs. We take the information from the cryostat. We take the information from the QPU, the figures of merit. We take the environmental systems, sensors. We pull all of that together into our database, and then we start running analysis on it. We apply learning models to it. We use machine learning. We try to attempt to see where we can find trigger points. So the idea is kind of several-fold. We're looking at this from an operation perspective, but then also from a research perspective for the stability of the systems as we move forward. For example, and I think kind of Matthias had mentioned this at one point, we have, as an HPC center, especially with Euro HPC, we have to sign a service level agreement. We are providing a service for Euro HPC to host these systems. We say, hey, these systems are going to be up so much of the time. Now, the vendor has a big onus to help us with this, but we also have to provide some stability and we have to provide some guarantee. And I can tell you that with nascent technology that's emerging, that's first coming into an operational environment, it's a little terrifying. Even as accommodating as Euro HPC is, it's a little terrifying to sign a service level agreement for something like a quantum system. And so we need to understand what is happening, what may be triggering from the environment, what may be triggering instability in the system. Can we somehow see those trigger events beforehand? Can we take that opportunity to see what's happening and then route the users to another system? Or, within the parameter that we can claim it as a scheduled downtime, we have to think about this. In addition, what we also want to do is we want to figure out if we can help with the QPU performance. So by having environmental noise models fed into the circuits, is this a way that we can also help optimize the circuit design to make them more dependable, make them more reliable, and make these systems more stable as we move forward? Okay, now here's another problem. Quantum software itself. That was the hardware, here's the software. What's happening in the environment right now, which is completely normal and completely understandable for this period, is that each company is a full stack solution. They have their own specific software stack. They go from the hardware to the software, the application layer, the users. Everybody has their own environment. As an HPC center, that's completely untenable. We're not going to be able to maintain that. We want to provide multiple systems, but we also have to be part of the maintaining of them. As much as the vendors may help, for us, it doesn't work. And so this is one thing that we have to keep very much in mind as we move forward. We have a lot of demands for what a software should do as we move towards a unifying software. And again, this is stuff that we've seen in the HPC space. In the early days of HPC, every HPC vendor had their own full stack solution. I guess for HPC people in the room, I can say something like Solaris, and you would understand. Before we end up moving, to kind of standardized Linux sort of environments, before we had kind of a general platform and a fat abstraction layer that we could work with. So we're going through this again, and this is where HPC can really help, I hope, Quantum speed forward and be really, get to the chase faster than we have in the past to be able to utilize this technology quicker and better and more expansively. So we have these software requirements with lots of things we have to think about. The different modalities. We have several different programming models, and Matthias also mentioned this too, several different programming models that the users for different domain spaces are used to. They want to be able to use it with the quantum environment. Can they do that? The physics environments are what Matthias referred to as the quanties. I haven't heard that before, but I like it. They're used to certain programming models, certain ways of coding. How can we bring them into the HPC environment in a way that's adoptable for them? For the HPC community, how can we bring quantum offloaders in a way that they will actually want to use and can use that does not disrupt their floor, where they don't have to do so much porting in order to be able to utilize those systems? So several different things we're thinking about here in this integration. It's a very complex, very multidimensional issue. Another issue that we have is what integration actually means. So right now, on the left-hand side of the graph, you've got a quantum system and you have an HPC system. And you have an HTTP connect between them. That's what's happening a lot of times. This is what happens in the remote space. All well and fine, okay? And sometimes this has to be the case because one system is one country, the HPC system is in another country, political, whatever. That's going to be a reality for some of these systems. That works, and there'll probably be work cases where that's just fine. Now, in the middle space, this is where we are now, what we achieved with Q-Exa. We have the front end, HPC. We have the compute nodes that do their work. When it's time to offload to the quantum system, it goes to that QAN, that quantum access node, where there's software there that does the coordination. From there, from the quantum access node, it goes to the control electronics, which then goes to the quantum system. All well and fine. We have a lot of use cases where we're starting to move in that direction. That works as well, but for us, that's an intermediate step. That may be an end stopping point for several. That's okay, but what we want to do is go all the way to the right. And that means that we use the HPC, that from every compute node itself, the compute node can call to the control electronics directly and can control the quantum node. And it's not just quantum node, I put that for simplicity, but it's really quantum nodes. We're also looking at how we bring in all the multi-nodes, not just multiple superconducting, but all those other different modalities that we talk to. So this is a fairly complex build. This is what we're striving for the right-hand side. Still have a ways to go, but we're working on it. That gets me to our Munich Quantum Software Stack. We had just last Monday, I can't believe it was last Monday, in Montreal, we had a tutorial where we launched the Munich Quantum Software Stack, which is our initiative with the Munich Quantum Valley, purposely to build that thick abstraction layer. We do this, I mentioned this before already, this is our Quantum Integration Center. This is basically where our target systems are at. So as I mentioned before, we have an ion trap, superconducting, the neutral atom comes in, the other systems will come in. This is really our target environments for our software development. Now, to the MQSS itself. This is basically, very simplistically, what the architecture looks like. On the right-hand side, you've got those quantum devices, the several different types. The first bar out to the left is a management interface that is really the backbone connect between those systems and the compiler environment. The compiler environment is based on an intermediate representation language purposely developed for quantum, and that allows us to connect with those systems in a way that the systems can understand. We've got figures of merit, which are the specificity of the unique physics of each of those systems, and I'll talk about that in a moment. And then from the back, kind of moving backwards, that's where we get to the HPC space. So on the far left, we've got the users, we've got their preferred programming models, their toolkits, how they interact coming from their domain spaces, but then they can do it either through an HPC environment that they're used to, or we are accounting for the fact that they are dealing with quantum direct, and so we have a web interface for that part. But either way, all of that goes into a scheduler on the HPC side that then coordinates, it does the selection of the systems, pushes towards the back with the compiler, pushes out to the systems. So it's a fairly simplistic, the baseline flow for the core, but again, because of the specificity of each of those systems and having to honor the physics, we have to have one level of abstraction above that, and that is what you see on these colored charts, or in these colored boxes. For each of these intersection points, these interface points, we have to have something unique towards the quantum system itself that we're dealing with. So ideally, and we've been working with several companies, well, actually, hold on, I'm gonna get to that in 1 second. Let me do this one first. The QDMI, this Quantum Interface Manager, this is a representation, again, another representation what I just showed you. On the right, you have the different platforms, you have the QDMI Manager, and this is going to allow in the compiling environment, it's going to allow the different passes to occur that are specific to those quantum systems that then push out to that device, get the feedback, and do this in iterative loop, so all of this is working together. Now, we have several companies that we've already been working with on this. Some of these are project partners, some of these are just partners from the MQV, but this gives you an idea of who we're already working with in order to have those back-end providers and to move this all forward. In the compiler space, we have a big toolkit team that's out of the Technical University of Munich. Many of you may have already been working with this, the Munich Quantum Toolkit that provides several of those compiler tools, some of the passes environment that really kind of bulks up that space and really helps drive us to have a multimodal quantum compiler that we can then connect with our HPC. So, kind of wrapping up, that was a super fast flyover. I could easily talk at length about this, as you can probably tell. I hope I wasn't too fast for you, but there's a whole lot going on. There are a lot of challenges. Once we've actually put these systems in an HPC center, I can tell you that our questions got a lot smarter and a lot more detailed. We were speaking very theoretically 3 years ago of what we would need to do and how to do it. Once we started getting these questions in, we realized that some of our assumptions were just completely out the window. We threw them. Some of them were like, yeah, that's okay. But really, we started asking a lot smarter, a lot better questions. So I hope that as we continue to move forward, we'll get even better at that. As you're bringing systems in to centers, you will experience that as well, and then we can exchange and hopefully grow together as a community. Now, I would be absolutely remiss to not thank my team. I affectionately refer to them as the Q crew at LRZ. This is not quite all of them, almost all of them, about 35 folks in general. And as Matthias also mentioned, an incredible collection of quantum physicists, of computer scientists, electrical engineers, mathematicians. Everybody needs to be part of this endeavor. I like to say this is us in the ground state, and this is us in the excited state. This is on the day that we launched Q-Exa for our inauguration. It was a really happy day because we really felt we really felt a sense of history, and we felt a sense of impact, that we're pushing this forward, that this is really happening. We still have a long, long way to go, but it's really great to have these steps. Now, this is my team, but of course, it requires many, many teams, and I just want to make sure that I highlight the teams of Robert Villa, the teams of Martin Schulz, unfortunately not on here, but then again, I mentioned before at the very beginning, MQV, that's the entire team from our last annual meeting. It's super exciting to be in this space because you really feel that we're on the cutting edge of all of this. And some of this is gonna work, some of it's not gonna work, but it's really exciting to be on this journey, and I hope that as we continue, there's more folks involved and we have more on the team. So thank you all very much, and I hope that gave you a little bit of perspective. Thanks.